onto this computer. Good. So we are recording. Welcome everyone to another QISS seminar, the last one before the summer. We'll be having Andrea Di Biagio, our postdoc in our group, in the same group as me with Marius Christodoulou. Andrea, will talk to us about Bell and Wigner and locality and friendliness and all of this interesting kind of stuff we love about quantum mechanics. Andrea, the stage is yours.
All right, thank you, Afek, for the introduction and for the invitation. So I will be talking about no-go theorems and actually different results. I thought because the QISS seminar is quite a wide audience, instead of presenting just one technical result, I will present a final result from me and collaborators. But before that, I would wanted to put this exciting area of research of the extended Wigner's friend scenarios in context within the broader scope of what people call experimental metaphysics, or like the Bell style kind of theory-independent results, and the quest of looking for an interpretation of quantum mechanics. And the story starts with a thought experiment. So I have a friend, he's called Emanuele Polino. He's a great experimentalist. He works in photonics. Right now he's in Australia. And I know that he's doing photonics experiments. And the kind of stuff he does is that he prepares photons in superpositions of polarizations, sends them down polarizing beam splitters, and one detector clicks and he records a zero in his computer, and actually does millions of these per second. But this is the kind of stuff that's going on. I myself, I'm not an experimentalist, I'm a theorist, and I just think of Emanuele and what he's doing. And even though I maybe don't have a full theory of what Emanuele's lab is like, I know kind of what kind of quantum mechanics tells me to do. I can imagine that he has a pure state. He has a state, Emanuele, when he prepares this photon in a superposition. And he's in a tensor state like that. And I use the Schrödinger equation to evolve the system. And I end up concluding that not only there is no definite outcome, but it seems like Emanuele is like entangled with a photon after the experiment. And so there are these two different descriptions somehow. The intrinsic description, where I'm pretty sure that Emanuele has seen something, but on the other hand, quantum mechanics doesn't tell me what that thing is, and even tells me something weird that is in a superposition, right? And this is obviously, most everybody who's here knows this is kind of the essence of Wigner's friend setup, right? And one is brought to question, like, is Emanuele actually in a superposition, right? Because every time I walk inside a lab, I don't see him in a weird state of being indefinite, or entangled with a thing. I just see him and his results. So maybe it's really just a problem that quantum mechanics somehow is incomplete, right? It has some, it describes the thing, but Emanuele has more information than me, and somehow I don't know how to update my state before looking in, and that's why I assigned to it a superposition. And it's not like nothing groundbreaking. Maybe it's just a problem with the quantum description. But if people remember the history of quantum mechanics, there was a moment that people had this similar argument with entanglement. This is the famous Einstein-Podolsky-Rosenberg paper, where they used the correlations of entangled systems somehow to argue that quantum mechanics was incomplete. That even though the state was saying that there was probabilistic outcomes to experiments, actually the experiments had to be determined. And so there was maybe locally the variable for API correlations. But as we know, then there is Bell's theorem, where actually it says, no, there is no locally hidden variable theorem, no hidden variable model. And something similar happens for Wigner's friend. So this is kind of the setup now, more stylized, with Alice is outside the lab, and she can do interference experiments on Charlie, we think. This is a development due to Deutsch, the people that studied the idea of Alice not just opening the box and looking what's happening inside to Charlie, but also imagining being able to manipulate it using quantum mechanics, full quantum description of Charlie. And some time ago, Czeslaw Bruckner had the idea of actually complicating this setup a bit more. And not only Charlie does a measurement on a quantum system, but this quantum system is entangled with a quantum system of somebody else outside the lab, this Bob here. And turns out that this setup, so Czeslaw here argued that this would be really pushing this idea of the measurement problem of Wigner's friend to a new frontier. And in fact, in the meantime, there's been no-go theorems showing that actually you can formulate some device independent, model independent inequalities, that once they're violated, you know that some metaphysical assumptions about the description beyond the quantum description have to fail, very similar to Bell. And actually, there's been a whole study of this kind of extended Wigner's friend scenarios involving observers being observed by somebody else and manipulated while being entangled with somebody else. There's a whole bunch of papers. Over here, there is actually a review. But somehow all of these theorems somehow together point to the central idea that there is something going on with observation, that somehow observations are relative. They're relative to the observer, like facts are not absolute. And this is the central theme of this talk, and we will look at one of these theorems concretely, the local friendliness theorem, and then we will look how this theorem fits together with Bell's theorem in constraining all the interpretations of quantum mechanics. And this is the first part of the paper, kind of introduction. And then the second part of the talk will be more concentrated on a recent result, focusing on the idea of causal modeling. And here we will see that there is another way of framing Bell inequality violations as a failure of causal modeling, which is a discipline that comes from outside of physics. And it's kind of forced historically to introduce the notion of quantum causal modeling or post-quantum causal modeling to find new causal explanations. And finally, our result is this idea that causal modeling, even post-quantum causal modeling, cannot explain the violations, these local friendliness inequalities, these inequalities I was talking to you in the previous slide. So let's get started. This is the extended Wigner's friend scenario, as we talked. And the situation is like this. Charlie's in the lab, is doing some measurement, gets some outcome C. And Alice, so Bob is on the other side over here, he has some input Y, like the choice of this measurement setup, and gets an outcome B. Alice also has input X and outcome A. And we collect the data that Alice and Bob collect from outside the box in these frequencies A and B. But we make an extra assumption. We assume that Alice sometimes, she just, in this case, when X equals 1, when her input, she decides to put X equals 1, she opens the box and she just asks Charlie what he saw, or like looks inside Charlie's lab to figure out what was the result. And is this constraint that A equals C? So we have kind of two probability distributions. Note that in principle, the value of C is not available on all runs, because in quantum mechanics, Alice can do some interference experiment in a way that kind of erases the value of C, like in the double slit experiment. And a theorem due to Cavalcanti, Weismann, and collaborators puts some constraints on these frequencies, these observed frequencies. The first one, as we mentioned, is this idea that observed events are absolute. So basically that Charlie has a definite outcome, but at every single run, even when it's not observed, and that the relation between the observed frequencies is a marginalization of some underlying probability distribution that actually happens, together with the constraint that when Alice wants to open the box, she can just learn about this value of C. So this is a constraint on this probability distribution P. Then we add a constraint of no superdeterminism, which is the idea that Charlie's measurement result is somehow uncorrelated from the inputs of Alice and Bob, which is kind of quite natural assumption, especially if the events are done in space-like separation, for example. So here you have a light cone drawing. If the events are happening space-like separated from each other, then there shouldn't be necessarily any correlation. In particular, these are free choices somehow of the experimenters. And then if we add the further assumption of locality, meaning that if you condition on everything in the past light cone of an event, you are basically uncorrelated from free choices on the side. So these are kind of another constraint on the probability distribution. And these things together put a constraint on the observed frequencies, these Fs, through this formula. These are called the local friendliness inequalities because the conjunction of these three assumptions is called the local friendliness assumptions. And these are violated by quantum mechanics. So if you treat Charlie as a quantum system, then the probabilities of Alice and Bob are stronger, like they have stronger correlations than the ones that are admitted by these three things together. And this experiment obviously has not been done on humans, but it's been done on smaller, simple systems. So already there are these two papers that do it with photons, and these guys do it with, I think these are superconductive qubits on quantum computers. And where the friends here are these small systems, right? Either a bunch of qubits, anyway, a bunch of qubits essentially. But if so we are kind of on a scale from like a real friend, like an actual person you can talk to, and nothing, we are quite far on this side of the spectrum. But what's important here to realize is that quantum mechanics doesn't tell you when it stops applying, right? In principle, we are made of atoms. Atoms obey quantum mechanics. In principle, if I have enough control, I could do this with a person. Well, we don't think we can do it with a person, but the theory, like in practice, we cannot do it. And maybe there's like no resources in the universe that allows us to do it with a person, but the theory itself doesn't forbid it, right? And people have been also making estimates of if we could use a human level AI, so some AI like ChatGPT that you could talk to for a while, convince yourself that they're sentient, even more advanced than ChatGPT, of course, and then put them in a quantum computer and make the experiments, do it with them. So let me compare this with Bell, because these constraints now, they accumulate these no-go theorems, right? So in Bell's setup is quite similar in a way. We have Alice over here doing her experiment and Bob over here doing his experiments. And one wanted, like, we wanted to explain the correlations by positing that there was something, carrying information from one side, from the center, from the source to the side, to the actual experimental setups. And so this idea that the observed frequencies of the experiment are somehow explained by being the marginal of a probability distribution over some hidden variable. And famously, Bell in 1964, I mean, I'm going to go fast on this, but just to summarize, showed that a conjunction of three properties, these are motivated by the practice of science and by special relativity. These three properties of this distribution here on the left impose some inequalities that, as we all know, are violated both by the theory and in practice as well. And again, we have no superdeterminism, locality, and we have the predetermination assumption in this first theorem of Bell, which is the idea that the measurements, the outcomes are, if you know the variable, the outcomes are deterministic. This was the idea that there was a further complete description. This was Einstein is often associated with this idea that quantum mechanics was supposed to be less random. That wasn't actually his point in the EPR theorem paper, but this idea that there was some deeper description. This is the local realism version of Bell's theorem. And we all accept that quantum mechanics somehow is a form of intrinsic randomness, so we're kind of comfortable giving up this idea of predetermination. However, something that I discovered quite late in my education, there is a second theorem of Bell that uses different assumptions. And in particular, it still uses the superdeterminism assumption, but it uses a local causality assumption, so it doesn't assume anything about determinism whatsoever. So somehow, even if you want to resolve the local realism problem by giving up on realism, as many people are comfortable with, you still have to face the second theorem, where now you're faced again with a locality assumption to give up. Your randomness doesn't really play a role anymore in this. And local causality is the idea that if you have these correlations, but you condition on this common cause in the past light cones, then the correlations disappear. So local causality is a conjunction of the idea that the causes are in the past light cones of the events, and this Reichenbach principle, also known as the principle of decorrelating explanation, which sounds a bit technical, but it's very natural. So if I have this correlation, what it means for something to explain the correlation is that if I know the value of that something, the correlation disappears. That is just pure randomness, right? The way that things covariate is completely fixed by this thing in the past. And so some people give up relativistic causal arrow. This is an example of Bohmian mechanics, pilot wave theory. But many people working on the operational quantum mechanics, or not looking for like hidden variable models, are forced to give up this Reichenbach's principle by giving up local causality. Okay. Now we enter this new stage, local friendliness theorem. And one of the assumptions, as we said, is the absoluteness of observed events is over here. Again, this is the idea of explaining the correlation observed by Alice and Bob by postulating some hidden variable. But this time, the hidden variable actually is not in play the role of explaining the correlation. It's just something we want to put there because we really firmly believe in this idea that observations are real. Or at least we're pushed in this direction by our intuitions. And then we have this locality assumption, superdeterminism give us the local friendliness inequalities. And these are violated not in practice yet, but in principle by quantum mechanics. And so having kept the locality assumption, the no determinism assumption, um, in the face of Bell inequality violations, we are kind of really pushed in this direction of giving up the absoluteness of observed events, which is quite a radical idea. And in fact, something also that is worth discussing at some point is that the absoluteness of observed events is also in a way underlying Bell's theorems, both of them, because of writing a probability distribution for facts relative to different observers. So like if you give up the idea that our observations are all equally real in a sense, how do we decide when we can mesh and write something like this and when we can't write something like this? So just a few more words about interpretations, although I did kind of anticipate some of these. So there are some interpretations that satisfy or somehow skirt all these theorems in the same way. The pilot wave theory, Bohmian mechanics, the Broglie-Bohm theory, they give up on locality. And so they kind of give up on this, they solve the Bell inequalities and the local friendliness inequalities by assuming that there is like a non-local superluminal correlation kind of thing. Then there are the superdeterministic models that it's no superdeterminism is just underlying all of these assumptions, so they all compatible with the thing. Everettian quantum mechanics, many-word theory, solves this thing by having different agents like doubling up, because of the branching, and then meeting the right copies of each other. There is a really fun paper called Parallel Lives that talks about this in concrete detail. What's interesting is the Copenhagen interpretations are actually pushed to drop different assumptions about reality as you move on. So we saw like the predetermination thing, the Eigenbeck's principle, and now absoluteness of observed events. Although some interpretations like relational quantum mechanics, cubism, Anton Zeilinger's and Joseph Bruckner's kind of informational interpretation, also Richard Healy, they all kind of already intuited the idea that facts were relative. But somehow this is kind of a vindication of these interpretations in a way, but also a further challenge, as I will come later to mention. What we cannot do anymore is just assume, that kind of there is like a overall notion of classical word that we don't have to worry about it. Like in practice, there is a classical word. If we keep pushing these experiments, bigger and bigger superpositions, eventually we're gonna start having to question this idea that, it is non-problematically a classical word. Of course, there is also another solution to this, which is actually maybe quantum mechanics fails at some scale. Maybe it's some mass or some complexity scale causes spontaneous collapse, or maybe consciousness comes into play at some point, like Wigner himself, when he proposed the ISOT experiment, actually wanted to argue. But this is kind of the map and the kind of reasonings these theorems make us do. So just a few remarks before moving to the next part. Maybe I already mentioned a few of these already, but the idea is this extended Wigner friend scenarios stand to Wigner's friend, like Bell scenarios stand to EPR, with this stronger, like theory-independent result, if you want. Another thing that I wanted to say, well, I said all of these things, so maybe I'll just move forward. But maybe one thing is like, if we want to say, but the experiments that we already done, obviously we shouldn't assign a variable to the friend because it's just a quantum system. We have to somehow find a principled way to make this argument because quantum mechanics doesn't tell us when a thing becomes a system. And then if we are actually wanting to give up absoluteness of observed events, somehow we have to kind of deal with this, I think, in a bit more detail. Like there's a lot of explanation to do. In particular, which one of these two mathematical formulas fails. And we'll come this on the very last slide. So now we shift gear and we talk about causal modeling. And this is a different way to see how both Bell's theorems and the local friendliness inequality violations challenge causal modeling, causal reasoning, in a way that actually doesn't depend on the idea of space-like separation. So these theorems actually have this behavior of quantum mechanics actually has consequences even when the experiments are done, in causal contact. A brief word about classical causal modeling. This is the idea of if you have correlations in data, you want to explain them, you want to find a causal model for them. And the causal explanation essentially is is a causal structure together with a probability distribution that is compatible with this causal structure. Where compatible means something specific, which we will come to in a second, but it's the idea of Markov conditions. The idea that if you condition on the direct causes of an event, then you kind of know everything you need to know, everything you can know about it. And there's several different formulations of this because it's been used in medicine, in economics, sociology, AI, robotics, many, many fields. One classic reference is this book by Julia Perl. And we can use this to model Bell's experiments. So you describe Bell's experiment with the particles flying in the different labs and so on. You also explain to the person that does this causal analysis that you observe this kind of conditional independence. So this symbol over here on the right means that conditional on knowing the value of X, there are no correlations between A and Y, the output of Alice and Bob's input. This is a no signaling assumption. But in fact, what's important is that it's not an assumption. It's actually something we observed in the data. Like, no matter how hard Bob tries, they cannot send a signal to Alice using Bell system. So this is just, it's a thing predicted by quantum mechanics, but it's also something that actually happens. It's a property of the data. So, all right, you describe the experiment, you describe this thing. The causal modeler comes up with this description. I mean, it's obvious. It's kind of like Alice's output can depend only on on her input and possibly on some hidden variable in the past. Then you use the Markov condition to create the functional form of a probability distribution that is compatible with this causal structure. And here you see Alice's probability is conditional only on her previous, like her direct parents, if you want, ancestors, and nothing else. And same for Bob and for the other parameters. And then you can vary the parameters over here, these conditional probabilities. You can vary them freely. And all of these probabilities are compatible with this causal structure. And what they all have in common is that they feature these non-signaling statistical independencies in the data, but also they all predict the Bell inequalities. And so because the Bell inequalities are violated, this model, this very straightforward causal diagram is not an explanation, is not a good model for what's going on in Bell. And this is true also not at space-like separations. Like the absence of the arrow between Y and A is motivated by the description in a way. There are classical causal models that can explain the Bell inequality violations. They look like this. For example, there might be a direct causal influence from Alice's input to Bob's output, or maybe there is a causal influence from the hidden variable to the inputs of the agents, or maybe one agent modifies the past by picking the input. And I put here names for these things, because they kind of match the assumptions in Bell. But this could be, this is not superluminal because it has to happen in space-like separation. It's just, all I'm saying is that there could be a causal influence from here over there. And obviously, all of these are compatible with Bell violations, as I say. They are in tensions with Bell's assumptions if we do this as space-like separation. But there's another reason why these are bad causal models, let's say, or at least they have something left to explain, which is this technical notion of fine-tuning. So these are kind of unsatisfactory causal models for a reason intrinsic to causal modeling or to themselves, which is this notion of fine-tuning, which I will take a couple of slides to explain. In broad strokes, the no fine-tuning principle is the idea that every time that we see some statistical independence in the data, this should be reflected by some property of the causal structure. So over here on the right, we have this deseparation condition, it's called. It's a relation between the nodes in the graph. And it's a graph theoretic thing. And the idea is that they are together. And this, because somehow I will come why to the motivation in a second. But just to give you an idea of what this deseparation relation is, A and B are deseparated by the node C. If C blocks all the paths from A to B, where blocking means something specific, which I will show if you don't have to focus too hard, but I just want to give you an idea that it's well defined. So if you look at all the paths that you could follow in the graph from A to B, and C blocks the path if there's only one way direction and you go through C, so it kind of C mediates the path. or if C kind of sits in a common cause, so you have to kind of go, back in causation to C and then back up to Bob. Or if the paths go through like a common node on the top, it's called a collider. And this node over here is not one of the descendants of C. It's a bit, it's a bit convoluted, this notion, but it's well defined. You can algorithmically figure it out. And so you have this graph theoretic notion over here of the separation, and you have some structure of the data of like the probability distributions compatible with the graph. And
Sorry,
yeah,
sorry to interrupt. Probably I
sure.
missed. What is the small d?
It's this separation relation. It's just a symbol to denote this graph theoretic
Not the
notion.
distance or something. Okay.
I don't know what D comes from.
Oh, okay.
Yeah. Right. So, and the reason that the symbols are picked similarly is because the Markov condition implies that to every D-separation relation follows a conditional independence, like a statistical independence relation. But the converse is not true. So if you have a graph, you can have probability distributions where two variables are statistically independent, but they're not D-separated in the graph. And the fine-tuning principle is the idea that actually no, to every statistical independence corresponds a D-separation and vice versa. And like this, somehow, because D-separation implies the conditional independence, if you ask for no fine-tuning, then somehow the causal model itself explains this decorrelation over here. And what's going on over here is that in all of these, for example, the output of Bob is not D-separated by the input of X. And in this sense, these things are decorrelated. But the important thing is that we don't see a correlation. So somehow to hide this, the idea of fine-tuning is that to hide this arrow, you have to pick the model very, very specifically. And so, yeah, you can postulate this causal explanation, but somehow then you are left to explain why we cannot signal, essentially. And actually, this is a result now, it's got, I think, almost a decade now, by Wood and Speckens, where they show actually that every classical causal model of the Bell inequality violations are fine-tuned. Like whenever you find a classical causal model that can explain Bell inequality violations, it's going to be fine-tuned. There's going to be one of these arrows that it's hidden by the specific choice of the probabilities. And the proof is quite simple. You look at the data, you look at the observations in the data, and the conditional independencies. No fine-tuning implies some D-separations, and then you can kind of combine them together, and the Markov condition just automatically gives you the Bell inequalities. So you don't have to search all the graphs, you just know it's like this. And the point is that fine-tuning doesn't depend on space-like separation or anything like that. So this is a difficulty in classical causal explanation of Bell. The solution they propose is to drop classical causal modeling and use quantum causal modeling. So instead of using Markovian probability distribution, you use a quantum probability distribution coming from a specific circuit that is implied by the causal model itself. And this proposal is precisely this idea of giving up local causality, but not by changing the causal structure, but by modifying Reichenbach's principle. So here, the common cause decorrelates A and B, but over here it doesn't. But it's a concrete proposal to amplify the notion of explanation somehow. Good. With this, you maintain all the statistical independencies. You don't have the Bell inequalities anymore. You have the serial sum bound instead, and you can explain all the experiments that have been done with Bell experiments somehow. Okay. Hope you're still with me, because now we are going to the actual original result that I derived with my collaborators, Ile Ying, Maria Marcela Anzanelli, Ali Wolf, David Schmidt, and Eric Cavalcanti. And actually, this is just one result of the many results in this paper, but it's the most exciting, I think. The idea that not only quantum causal modeling cannot explain Wigner's friend scenario, but even post-quantum causal modeling. So it's an even stronger challenge. Concretely, one word about post-quantum causal modeling. There's been several generalizations. Instead of having a quantum common cause, you can have a post-quantum system, in particular with, for example, generalized probabilistic theories. If you don't know what these are, it doesn't really, nothing much hinges on it. You can just think of everything as quantum. But the idea is that to every graph, you can associate, there's this generalized Markov condition that associates, okay, sorry, it's written like this. It's a bit complicated, but the idea is that you associate a circuit, either a quantum circuit, or if you're doing post-quantum, you can use a GPT circuit, and where the hidden variables, sorry, the latent variables, they propagate quantum, some post-quantum system over here, and these are measurements you do on them, and so on. And we applied this to the local friendliness scenario. So again, if you describe the experiment to somebody together with the conditional independencies you observe, they will come up with something like this. So here there is a latent node that is a general quantum system or post-quantum system that gets distributed, that can influence Alice's output, Bob's output, and Charlie's input, and so on. And using the generalized Markov condition, you get a circuit, and you get a bunch of probability distributions that are compatible with the circuit. And here we also have an extra constraint, which is the idea that Alice can open the box and see what Charlie has. So these are all we don't take all the possible probability distributions, but the ones that are at this extra constraint on this POVM over here. Well, POVM if it's quantum mechanics, but with this measurement, if it's a generalized probabilistic theory. And you look at all of these things, and okay, again, they give you these no singling properties that we observe, or quantum mechanics predicts at least. But they also give you the local friendliness inequalities. And so this causal structure, no matter how general this system is, doesn't give you the correlations predicted by quantum mechanics. Again, there are alternative causal models of this form. So we have extra arrows, again, very similar to the situation with Bell. And these all allow for the local friendliness inequality violations, but they are in tensions with the local friendliness assumptions if it's done at space-like separations. And even if it's not done at space-like separation, they are bad in the sense that they are fine-tuned, again, just like in Bell. And we managed to prove a very similar theorem to the Speckens one, which is that all models, all GPT causal models that can violate the local friendliness inequalities, they do it so via fine-tuning. And the proof is exactly very analogous. We have these observed statistical independencies. No fine-tuning gives you a form for the causal structure, or some constraints on the causal structure. And then the generalized Markov condition in turn gives you some constraint on the probabilities, and it gives you the local friendliness inequalities. There is one technical difference, is that in Bell, these two first conditional independencies are actually observed, whereas in quantum mechanics, in the setup in which I proposed it to you, you don't really see the variable C on every single run. So this is not present necessarily in the data. And you can do two things. Either you just assume that it's kind of reasonable that C is independent from X and Y, because otherwise it's some sort of retrocausal model already. Or you do something a bit wilder. This was proposed to us by Veronica Baumann. That's why it's called the Veronica protocol. And you cannot really, what you can do is that you enlarge the lab, you make it a bit bigger, and you put another person in here, a verifier. And instead of doing an experiment with only one friend at a time, you do the experiment with a whole bunch of friends. And before Alice does her measurement or not, the values of the setups get distributed inside the box, and Veronica checks the data, and she can empirically check that C is independent statistically from X and Y. And we show in the paper that this can be done. Without Veronica getting too entangled with Charlie, and then you can do some stuff to them and disentangle them again, and then eventually Alice can actually perform her experiments while having received this message that the measurement of C was independent from X and Y, and validate the local friendliness inequalities. So this is just a technicality, but again, if you take this for granted, then the result follows through, or you have to modify the setup, make it a bit more complicated to actually have this thing. All right, I'm still not good with time, but I only have a few slides left. So as I said, this is a paper. It's quite long actually, and we do more things in this paper. So I invite you to read it. We show in a much simpler setup that the local friendliness inequalities are monogamy relations, between the correlations that Alice has with Bob and Alice has with Charlie. Somehow, Alice needs to be correlated with Charlie sometimes at least, but she also needs to be correlated with Bob all the time. And this double correlation has some limitations. And you can just get the local friendliness inequalities from monogamy relations and no signaling assumptions. And then actually I had these GPT causal models on the slides, but actually we have something much more general. It's called, we invented it actually, it's called the, I think we invented it. It's called the disseparation causal models. It's just whatever model that to any disseparation follows a conditional independence. This could be with Markov condition, generalized Markov condition, or some other rule to be invented. But as long as a model has this relation and you ask for no fine-tuning, then you get the theorem. And actually, this can also be generalized to cyclic causal model, like a large class of cyclic causal model, both ones that exist already and possibly ones that are to be invented. Again, if there is some sort of graph separation relation that implies conditional independence, even allowing for causal loops, then this implies a fine-tuning principle for cyclic causal models, and then all cyclic causal models that can explain the local friendliness inequalities have to be fine-tuned by their own definition of fine-tuning, just in a sentence. So this is going to be the last slide. And so just to recap somehow, I showed to you this extended big friend scenario and this theorem, a no-go theorem. Also in the causal explanation, somehow it was important to have this node C and the assumption that C can be read by Alice. And so I was kind of saying that we are pushed in a direction of giving up this idea of C taking a value, or at least this notion of absoluteness of observed events, which in the theorem takes this form, a constraint on the probability distribution that we don't observe. Actually, two constraints. One, that the observed frequencies are the marginal of this unseen probability distribution. And the other one is that Alice can actually copy the result of Charlie. And one kind of there are several proposals, and one should analyze them and kind of see technically what's going on. And I just have a selection here. One way to get out of this assumption is that actually maybe this really is a marginal somehow of another probability distribution, but when Alice opens the box, somehow she's disturbing this very delicately created quantum setup, and she perturbs the value that Charlie saw. And so actually she thinks that she's reading what Charlie saw, but actually maybe she changed his memory or something like that, and the act of the observation actually perturbs Charlie. On the other side, there's a notion of, there's a way out, is kind of duplication. So this is not the conditional, it's not the marginal of some probability, because actually maybe inside the box there are two Charlies all of a sudden. This would be the thing that happens with the Vertian quantum mechanics, like with many words. There are two Charlies for a while in there, and you cannot have you just can't say what the value of C is anymore, because there are two C's. And in the case, in particular, in the model of Vertian quantum mechanics, the violation is due to these two words kind of recolliding and getting interfered. And this is explored by my colleague Caroline Jones and Marcus Müller in this paper in classical duplication. So outside of Vertian quantum mechanics, just this idea that these theorems somehow are not super quantum, but something to do about maybe duplication. And on the other side, there is this discussion about how this duplication can allow for both the violation of for the violation of Bell in this case of this paper over here. But as I said, if we give up absoluteness of observed events, because this is an assumption in Bell, we can kind of revise how we solved Bell in the past. And yeah. And then there's a third way, which is the relative facts way, which is the idea that this is not a marginal. So the data is not a marginal over a real probability distribution for several reasons. But in particular, somehow that maybe there is a definite fact for Charlie, but the relation between relative facts to Charlie and relative facts to people outside is not necessarily marginalization. Interference is kind of the symptom of relative facts. Or another way, like in relational quantum mechanics, we like to say, Carlo Ravelli makes this point often, when we work together, that if you wanted to know what Charlie's value is, if you want Charlie's variable to have a value, then what it means for it to have a value is that you asked Charlie and you got information from Charlie. And if you don't ask Charlie and you do an interference experiment, then it's kind of your fault and you're never gonna know, because quantum mechanics allows for facts to kind of dissolve into nothingness. And with this, I close with this slide, and I thank you for your attention, and I'm open to questions. I guess that's how it works here.
Thank you, Andrea.
Actually, before the first question, I want to say one thing I forgot to say is that maybe one way out of this, also like a general idea for the community, is that the way that we generalized from classical causal modeling to quantum causal modeling, maybe there is a generalization of causal modeling that allows for different contexts, like not having Charlie's result and Alice and Bob's result on the same level, but somehow still having them, but on different levels. But this is to be explored. And yeah, if we want to get out of the idea saying, oh, there is no problem because the photons are not friends, then we somehow have to look into the idea of like starting to look at modeling observers quantum mechanically and trying to understand when it's possible and when it's not possible to do interference and so on. All right, sorry for the double stop. Thank you.
Good. So now we're open for questions. Please raise your hand if you want a question. The first one is Alexei. Please, Alexei Greenbaum.
Yeah, thank you. Thank you, Andrea. Thanks for the talk. When I think about the condition of fine-tuning or no fine-tuning, it really comes from I think epistemology, from what it means to have an explanation that is really explanatory, explains something. And if this is correct, I mean, what is your thinking about the condition of fine-tuning? If this is correct, then it seems to me that fine-tuning comes before the determination of events. So we want to have an account, it's not that we put events and then require no fine-tuning, is that fine-tuning is a precondition to defining events. So in that sense, it would be interesting to say, okay, under the condition of no fine-tuning, what are all possible causal models by redefining events in different ways for merging these things, separating them, and so on. Has this been tried, redefine events as a consequence of a no fine-tuning assumption?
That's a really good point, Alexei. Thank you. To my knowledge, I don't know if this has been done, but I see like the idea somehow is that because all models with C are fine-tuned, somehow we are kind of pushed into looking for models that don't have C, or at least have C only sometimes, or something like this, I guess. Because if you take away, I have it here. So in this graph, if you take away the node C, or you take away the condition that C has to match A sometimes, then you can, of course, explain this with quantum causal models, right? Because in the end, the predictions of quantum mechanics are precisely given by a graph where C doesn't exist. And so yeah, when we were writing the paper, we were kind of considering like, is there like sort of dynamical notion of what models are allowed or not, depending on whether C gets acquired or not. But no, to my knowledge, it hasn't been done, but it's possible that somebody's working on it.
Okay, thank you.
Can I ask a question? You hear me?
Yes, Nathan,
Perfect.
but
This is
there is
Nathan.
a line.
Yes.
So you will be after Carlo, okay?
Okay, great.
So the next one is Jaslav, please.
Hi, Andrea.
Hi, Jaslav.
I hope you hear me well. Can you go back to the slide where you comment on absoluteness of events?
Yes, sure.
You lay down kind of three possibilities.
Yeah, it's not exhaustive, I must say, yeah, but just...
Yeah, so what I think is this disturbance can be even relaxed. And still you can derive a non-trivial bound, namely, as long as the disturbance is local, this will not give even explanation of the data. So in the original local friendliness, it's indeed written like that, that when you open the box, you have to see what was in the box, so to say, before. But even if there is a change, I think it's still possible to get non-trivial things as long as this change is locally produced. And so, in a sense, hinting that only possible solution, if you still want to talk about absoluteness of some events, existing, is that these, when you open the box, maybe you can influence even the events which are far away from you, which hints into some kind of non-local explanation. That's one thing. Maybe it's useful to think. I mean, I'm thinking about that, and I think originally when I was thinking about that, I was thinking that way. And the second about these relative facts, I feel like, of course, this inequality that is written, it's the way how I also understand things, yeah. That when you measures FAB given XY, it's not by marginalizing some joint probability. But I think it's very tricky in a sense that if you accept that all agents are equal and they do perform their measurements, there exists really the joint probabilities in all the cases when everybody measures his, her own setting. So there is a joint probability. It's not that it doesn't. It's just that the way when you open the box, you will not marginalize. So it's really, I feel that relational quantum mechanics is the way, or I don't know, only relational, probably Cubism and maybe Neo-Copenhagen will go in the same way in understanding why there is no equality. But I would like to add that there are good reasons not to abound the existence of joint probabilities in the case when all measurements are performed. I don't know what you want to comment. I would be happy to hear.
All right, Czesław, thank you so much for these comments. So yeah, you said many things. Let me start with the first point and then I'll come to the second. So actually, I had heard this from your students and I didn't want to put words in your mouth. I thought it was also kind of your idea. So, but yes, I agree. Like this doesn't have to be, it's kind of local, right? This is Alice, she's interacting with Charlie and she's modifying Charlie's thing. I think that's what you mean by locality, right? And in fact, in our paper, we say that if you relax this, it doesn't have to be totally random. The amount of noise, if you want, or an amount of disturbance that is there is kind of directly linked with the strength of the violation, right? I don't remember exactly the number for this, but I do remember now that we are talking about this, that there is a paper on quantum, published on quantum by people at IQFO, I think. I don't want to say something silly, but it's called sort of like quantum mechanics is maximally non something, and the idea that somehow the violation here can really, really be strong of this in some setups. But I don't remember. People, this can be made quantitative, and I agree it needs to be local to the person. And so you can have this fact, but somehow when you interact with the thing, it goes away, or you kind of make a mess. And this other point about having a probability distribution, I agree. Like in principle, nothing forbids you from writing down a probability distribution. But then the question is whether marginalization is the way to go from this to this, right? And I mean, I had this argument with Carlo many times, and like, the idea is like, somehow there's an idea of like, okay, Charlie's measurement result cannot be obtained on most runs because we're doing interference experiments. But if we really, really want to have it in our kind of ontology, like if we want to fill the world with this unobservable fact, we can do it. And it can have a probability distribution, but we're just forced to either have these non-localities or kind of the failure of probability theory in a sense, because marginalization is quite basic notion in probability theory. Sorry, did you say something else about this second point?
No, I fully agree with you. Yeah.
Right. And I called it. Sorry.
Yeah.
I called
No. I mean, it's very hard, I think, to avoid under these conditions that we talk, some kind of, if you want to talk about joint probabilities, and there are really good reasons why to do that, because everybody can say, I see a definite outcome to some outside observer. So if you give this right, and if you want to talk about that, it's somehow very hard to avoid non-locality.
Yeah,
Yeah.
right. Yeah, which is goes with intuition many people have that there is a fundamental irreducible non-locality.
Yeah.
In a
Or you
sense.
can choose not to talk about, and then you can say just these things. I'm not interested in a box if I don't open the box.
Right. Yeah, I shouldn't be talking about what's going on inside. Or like wondering what actually is inside. Because if I want to know, I can open and check. But then if I do something else, then it's kind of my fault if I don't see it.
Yeah.
Yeah.
Thanks. I mean,
Yeah. And I also
share
want to
your
say I
opinion.
made this column called the relative facts, or I didn't tie these solutions to any particular interpretation because I think different interpretations could go one way or another depending on the details. So, yeah.
Thanks.
Please, Nicola.
Okay. Hello, Andrea. Can you hear me?
Hi, Nicola. Yeah.
Hi. So I really liked your final comment on the fact that there is a possibility of generalizing causal models to quantum. There is a possibility of understanding correlations using classical causal models and stuff like that. But so on this point, exactly, there is a third way, which is the one of understanding causality as structure of contexts in itself, in a way, in the way, in a specific way, causal models then just be the case when there is only a kind of a global context where all the inputs are contained in this kind of global context. And this is what we try to do with Stefano Gogioso, and there are some works of ours on the archive if you want to check this. I don't want to advertise my own stuff, but just because you kind of mentioned this third possibility, this third way, I really much agree. This is, I believe, a totally different kind of perspective on causal modeling, where you take context to be primitive in a way. Thank you.
Cool. Thanks, Nicola, for the comment. And sorry that I wasn't aware of your works, so I thank you for pointing them out to me. Can I actually ask you a question back? Like, is this somehow related to what Alexei was saying? That somehow, in a way, like we don't know, maybe it's not that related, or more related to the answer I was giving to Alexei, that somehow like the reason that there should be a node there really depends on what's actually going on the boundaries of the process. And like if Alice doesn't do the thing, then the node can be there, but if Alice does the thing, then the node shouldn't be there. Is this related in any way, or?
So I think that the problem with kind of classical causal modeling is this idea of the nodes in themselves, right? So there are these kind of variables which are the nodes which kind of interpret the causal effects between these kind of variables, but there isn't enough structure to carve out the context out of these things, because the contexts are structured of collection of choices, right? So it's kind of it's as if you project down everything into the classical case, but because like this is what Judea Pearl's kind of primal assumption was, like that fundamentally causality is a kind of definite relationship between variables obfuscated by some ignorance, right? But in the case of a kind of contextual model of causality, then this kind of randomness is fundamental, so it's inscribed into, yeah.
And the existence of the variables themselves somehow depends on the context, right? That's kind of also part of it.
It could, yes. If you can have a fixed causal order where the variables are always existent independently in the context, so you can have situations where the existence exactly depends on the choices. So maybe even modeling is kind of in a different situation. I never tried.
Right. Have you tried like hard disk paradox or double slit experiment or something like that?
Yeah, there are several ways that can be modeled in this way, like from Legge-Garg to all the kind of non-locality paradoxes.
Cool. We should talk. I'm interested.
Absolutely.
Thank you.
Please, Carlo.
Hello.
Hi, Carlo.
Very good talk as usual. I wanted to ask something just about the motivation
Sure.
of post-quantum models.
Hmm.
So we have these post-quantum models, and they give us violation coefficients for Bell inequalities, for example, and these are different from what quantum mechanics gives us. And of course, like we made the experiment, and it ends up that we know that quantum mechanics is correct. So I wanted to ask first if these post-quantum models give different values for these local friendliness inequalities, if you show these, other than what quantum mechanics gives, and then if you have some reason to hope that it is interesting to look at these models. Like, do you believe that maybe we will measure something different than quantum mechanics predicts, or why would you look at that?
All right, thank you. So this is kind of a general question of like, why do we build new theories before having data for them somehow, in a sense? And so first, the easy answer, yes, they probably do have a stronger violation of local friendliness inequalities, but we didn't. It's not as if we plugged in some real GPT and checked it. So the answer is I don't know, but I would be ready to bet that they do provide stronger violations. Another thing is, yes, I mean, for now, all experiments are compatible with quantum causal modeling, I guess. And I guess I don't really know the motivation that there was to develop post-quantum causal models, but I guess once you have post-quantum theories, GPTs were developed, I think, primarily to try to understand what was weird about quantum mechanics, what was special about quantum mechanics in the context of reconstructions. I guess once you have something like that, you might as well, make a quantum causal model, like post-quantum causal models, and see what the limitations, maybe there is reconstructions that could be made with this. But in this context, I think this is kind of I guess our result in a way is kind of a vindication of developing this thing, because here is a situation where, okay, quantum mechanics tells us something weird about the world. Can we try to explain it? What's the most powerful general thing we can use to explain it? And it was kind of already developed. And so we just took it off the shelf and proved the theorem about it. Two things. Did you say one more thing? What I think would happen with these experiments? I presume that it's going to work somehow. We're going to make bigger and bigger things. I know people are working with much bigger than 16 qubits. I don't know if I can say who and when, but I know that people are pushing this. Just last week in Helgoland, we were looking at Marcus Arndt's talking about doing interference with like enzymes and like pushing towards viruses and so on. So like we're gonna explore the limits of quantum further and further. And I don't think anytime soon we're gonna do this with a person. I think actually there are some like de facto limitations on how big a system can be to do meaningful interference. But anyway, I think this is really a problem with defining the notion of when does something happen. And this is why I'm interested in this kind of stuff. Like when are we safe to say in quantum mechanics that something has actually happened? Hope that answered your questions. Okay.
Nathan, please.
So I think I have two things to say. One is that I'm sort of confused about this role that Charlie is playing. If Charlie is really just not a person, but just a system of a number of qubits, then we can't assume that there's a measurement there, because a measurement involves decoherence of the results of the measurements, right? So Charlie will be another quantum system rather than an observer, and the assumptions you make about observer will not hold about Charlie. So that's one question I would like to ask. And then let's first
maybe I answer this question first, because it's been difficult
not to complicate
to
things.
questions at the same time. So this is a really good question that you're asking, and I kind of hinted at my answer already in one of the slides, which is somehow quantum mechanics doesn't tell us what is an observer, right? It doesn't say like, okay, it needs to be bigger than this, it needs to have a Kolmogorov complexity bigger than this, or whatever. There's no concrete rule. There's no postulate of quantum mechanics that tells you what causes the collapse of the wave functions, let's say, or what makes facts become definite, right? And yeah, there is this story of decoherence, and decoherence when a big system kind of gets in a superposition of positions, it's interacting with all the gas molecules that are around it, and they're getting information and fast, like really fast. You cannot do interference experiments on the needle of a measurement device, say, for example.
Right.
But these things rely on unitary quantum mechanics, and the decoherence is always effective and always never finished. Like in principle, you could always gather all these gas molecules together that are all complicatedly, like delicately entangled with your system, and kind of unitarily undo the entanglement and the decoherence itself.
Right, but I think the assumptions that you make about observers are only relevant if the decoherence is actually complete, which means
But the
that
coherence
in
is
your model,
never.
no, that's
The coherence is
practical.
never.
That's a practical matter. Decoherence is never complete in practice, but in theory, you can add a heat bath and take the number of degrees of freedom in your heat bath to infinity, and then decoherence will be complete in your model, and then you are justified to make these assumptions.
Right, so it's the other way around, right? So the coherence is only ever done in practice. Like in practice, all of a sudden, I don't have control anymore to do it. But in theory, it's never complete. Unless, yeah, if you have an infinite,
Yes.
maybe you have this, but nothing is.
You have to use the mechanism that quantum mechanics allows us to introduce irreversibility, which is called the heat bath. And if you introduce a heat bath, then you can have complete decoherence. And I think that's when your assumptions are allowed.
A heat bath, I mean, I agree. Like when you have complete decoherence, then the assumption goes through, the local friendliness inequalities are not violated and so on. But we need to remember that a heat bath is just an idealization of an actual physical system that has finite number of atoms in it, and therefore doesn't have these super selection sectors that come from the so-called thermodynamic limit n goes to infinity. Like that's a thing we do because we can always approximate the behavior of big systems by behaviors of infinite systems, but we shouldn't forget that these are like modeling assumptions. They're approximations to
right,
the reality.
Yeah, of course, yeah.
But then you and me are not made of infinite number of atoms, but we still think or feel like we're not in a superposition, and we still think and feel that everything we read are, if I buy a book and I read something in the book, what's written there is objective, not relative to whatever I did.
Of course, right.
But this is true regardless of the fact that we are not in contact with a really infinite heat bath. And whatever decoherence happens by these kind of arguments using unitary quantum mechanics is never complete.
Yes, but I think extrapolating quantum mechanics to the scale of humans is we cannot even confirm quantum mechanics on the scale of the Planck mass. So extrapolating it to the scale of humans is very it's speculative anyway.
Yeah, I buy it. I mean, I mentioned it as one of the possible resolutions of this thing, that somehow there is a place where quantum mechanics actually fails. But this problem that I'm showing here is a problem with the theory, with quantum mechanics as we know it, and its implications.
But it's because you are avoiding making the measurement an irreversible process. You have to accept that measurements are irreversible. Otherwise, you won't be able to. You will get paradoxes.
Nothing is truly irreversible.
No. So if we are talking, we're sending signals to each other. If you believe in complete reversibility of everything, we should be able to signal to the past as well.
Given enough computational power, yes.
So that's like, that's arranging things so that they will happen. So if you have enough computational power, you can make the entropy of a small system go down, right?
Yeah. Well, we do it.
But
we uncooked eggs.
So yes, but
we can do it. So the point is somehow is like I'm saying the theory does not forbid something like this to happen that I'm describing. I'm not saying that this happens. You go to the supermarket and this is happening, right? Like this would be like a very difficult experiment to do, to the point where I say probably it's not going to happen with a person, but we're going to do it with bigger and bigger systems. And I don't see a fundamental limitation, honestly. If we are actually going to build quantum computers, I don't see a limitation to do it with something that, like, I don't know, even like a video game. You know, it doesn't have to be real people, but somehow it really pushes this notion of like, when is it safe to talk about something having happened? Because if I have enough power,
But I think
mechanics tells me I can
yours.
reverse it.
Sorry, I want to chime in because this question is becoming very long. You could discuss this, both of you are in Vienna now.
Right.
Yeah.
Also, yeah, I think there was a little maybe misunderstanding in the language. The irreversibility that Nathan means, as far as I understand, is the same irreversibility that you get when you assume that time flows only in one direction. So, and he says signaling, he means that I can signal to the future, but it's not a matter of computational power to signal to the past. Uncooking an egg is not signaling to the past. And yeah, just wanted to make this comment, but think about it and talk later. Now, please, Marius.
Okay, I don't have anything smart to say because I only superficially know this story, but I wanted to ask Andrea about the experiments that you were chatting before. So, from Bell's theorem, Bell's theorem is so famous because we call it experimental metaphysics, right? You can actually show that some kind of class of theories that intuitively we would have liked to have, maybe you cannot have them. You need to lose something. Now, here, is it the case indeed that in order to use this type of inequalities to learn something about how you can model the world, you would have to actually put in quantum superposition a sentient thing like an observer, or is there a way around it, in your opinion?
Right. Thank you, Marius. Now, this is a really good point, and I think it needs to be discussed. It's been discussed. So I'm going to go back a bit, quite a bit. Okay, I'm here. So, no, wait. Why? Sorry. This is a bit. All right. So, good. We're here. So, yeah. So far, it's been done with very simple systems. And obviously, nobody's shocked that you can violate the Bell inequalities using a qubit, a photon. Nobody's shocked that you can do it with 16 qubits. The question is, when will we be shocked? And somehow we don't have an in-principle way of knowing when we are going to be shocked. Of course, if we were to do it with a person, I think we would be shocked. You say a sentient observer, of course. And
But
somehow,
the question is somehow, do we lose the absoluteness of events given the realization with 16 qubits?
so the question is, what counts as an observed event? And that's something that we don't have a definition of in quantum mechanics. And okay, one way to do it is, okay, a person is observer. Okay, is a mouse an observer? Is an amoeba an observer? Amoebas make decisions. They sense their chemical signals on their skin and they decide whether to go left or to go right. Like, is any kind of small program that makes decisions with inputs an observer? Like, we don't really, I think all these are kind of, somehow there's no strict place where, observerness arrives, and it's kind of a continuum. And we can build different measures of observers, of friendliness. We went to a conference organized by Unitary Foundation with Zhang, one of the authors of this paper, and collaborators, also Cavalcanti and Howard Wiseman were part of the organization. And there it was we were all sitting down and trying to decide what was a good definition for what a friend is, what an observation is. Czaslaw was also there. We're talking about kind of thermodynamic measures of entropy somehow, or branching factors, like how complex is the branching structure of the state. This is what was used here. And the answer is that there's no full-blown answer, like when do we lose observer events?
And just, I haven't followed it, so maybe the question is, and why doesn't some kind of, memory or registering that count? There's something more, obviously, that you want.
Well, because a memory is anything that you can write down and read back later. And so a qubit can be a memory. And in fact, qubits would be, qubits in a quantum computers are memory registers. So by some definition of memory, we've already done this. What we want, what you're intuitively pointing to is somehow something that has an internal state and it's got some parts of the degrees of freedom that are correlated to past events that happen to it, and it can use those to make predictions about the future, sort of thing, like a minimal model of an agent. And this is not what's happening over here, but in principle, there's nothing stopping from doing something like this with like 5 or 6 qubits. Maybe that's too little, but like say 40 qubits, I think you could have a minimal program that makes
I'm
this.
trying to get my head around this. Why not then take the experiment with the qubit as proof of, that you need to lose absoluteness of events, given that.
Yeah. I mean, when these papers came out, Carlo and I wrote in a paper that this is proof that facts are relative. but then, it's like, yeah, but it's not observed. Like, I mean, actually, I should point out there is a really nice paper by Wiseman and Cavalcanti and Eleanor Riedel. No, what's it? Eleanor Riffel. This one goes a bit more in the of like, so it's thoughtful is in like this inverted commas, because it's really the idea of exploring somehow what could be an observer. And this is where they explore the computational cost of having to do it with an AI. This is a very interesting paper if you want to read it, kind of philosophical, but it really goes in that direction that you are pointing out.
Okay, thanks.
Welcome.
We have so we have in the chat 2 comments by Alexei and that are pointed at Nicola and Andrea and to Marius. And we have one last question by Giacomo Papani. He asks, how does the possibility for Alice to check out the result of Charlie and being certain about Charlie's outcome relate to the no-go theorem of Frauchinger and Torena?
Right. So the no-go theorem by Frauchinger and Renner is about different agents reasoning about the reasoning that other agents are doing and taking conclusions from their conclusions about these other agents. So it's a bit more convoluted than just asking. So in here, when we say that Alice is asking, she's literally just, we're talking about the physical interaction. She opens the box, she looks in, the photons are rushing into her eyes, and she's learning the value of the observable, or like, she's hearing something. In the Frauchinger-Renner experiment, it's more abstract what's going on. There is a super observer outside, and they know what's going on inside the box, and they know what the friend inside, Charlie, is doing and what he knows. And somehow they put themselves in their shoes. They kind of look at what states Charlie would assign to other observers, and then uses the probability distributions that Charlie derives for themselves. So kind of taking probability distributions out of the box. But this is all happening inside somebody's head. There's no physical interaction. So I think there's actually quite a big difference between these two protocols. What's not different is assuming that there is something going on inside the box. So that there is a definite something. In our case, is the value of the measurement. In the case of Frauchinger and Renner, is the outcome of the experiment and also the things that the person is thinking. So there's a connection there, but Giacomo is asking specifically about the possibility of reading the outcome and being sure about it. I don't know actually how much that is used in the Frauchinger-Renner experiment. I think this all happens without ever Alice actually looking inside the box. She does all this reasoning. Maybe she does interference experiments on her friend Charlie, but she doesn't actually ask Charlie her outcome, I think, in most protocols. So they're related, but they're not the same, I think, off the top of my head right now. And if I may, I would like to react to Alexei's question, which is great, actually. It's like, yeah, the Bohrian, like Bohr says, what's classical? You want to say, Alex, you want to say it yourself? Huh?
No. Go ahead. Yeah, I was saying in the comment that, whether it's a qubit or 16 qubits or whatever, I think we would be shocked if Alice, when she opens the box, could actually speak classically, communicate with Charlie rather than make a measurement. And that would be kind of, a Bohrian surprise. So Bohr, of course, didn't insist on any physical composition of observers, but insisted on their capacity to communicate in an unambiguous way. And that is the defining feature.
That's great. It's a really good. I didn't think of putting it in these words, but it's great. And it's actually kind of the direction they take here. Not explicitly. I think they don't explicitly motivate it via a Borean thing, but it's precisely this. Like, if I can talk to them and I feel like they understand me somehow, I should implicate more like reality to their experiences, sort of thing. But here you're talking about when can we actually use classicality. It's not about necessarily about conscious experience, right? It's really about the minimal context, the minimal thing to be part of the classical world is that we can communicate to each other.
Okay. This was very enriching, a very enriching question session. So if there are no more questions, we will thank Andrea one more time using the clap emoji. And thank you all. We will see you in the next QISS seminar, which will be probably after the summer. So have a great summer.
All right. Thank you, Afek. Thank you, everybody, for the discussion and for the attention.
Bye.
Bye-bye.
Bye-bye.